Hello, my name is Kelly, and today I'm going to be giving my presentation on acetylcholinesterase. So what is acetylcholinesterase? Acetylcholinesterase is the catalyst enzyme of acetylcholine. It's primarily located in the neuromuscular junction of skeletal cells and between the nerve endings all over the body. It's one of the most efficient enzymes in the body with a turnover number of 1.5 times 10 to the fourth molecules per second, meaning it can catalyze up to 25,000 molecules of acetylcholine in a single second, which is incredibly fast. So its principal role with respect to function is to terminate the neural impulse transmission and signaling in the synapse between the presynaptic and the postsynaptic neurons in the body. It also catalyzes the degradation of acetylcholine in the neuromuscular junction, as well as preventing acetylcholine dispersal and activation of nearby acetylcholine receptors. So here we have just a small depiction of our neuromuscular junction with our presynaptic neuron here on the top, our postsynaptic neuron here on the bottom, and the synapse here, which is the space between the two neurons. So typically when when an action potential is generated, we have an influx of calcium up into the presynaptic neuron, causing the formation of acetylcholine, which gets trapped in these vesicles here. As the vesicle fuses with the membrane of the presynaptic neuron, they get released into the synapse where they bind here at the bottom with the acetylcholine receptors. This is the space that acetylcholinesterase basically inhabits. And what it does is it acts like a little Pac-Man, and it comes along and it gobbles up all of the extra acetylcholine that occupies the space in the synapse and forms acetic acid and choline. And this is extremely important because too much acetylcholine in the synaptic cleft can cause toxicity within the body, which can lead to cramps, muscle weakness, paralysis, blurry vision, and even death in extreme cases. So our catalysis reaction of acetylcholine is basically a hydrolysis reaction, where acetylcholinesterase breaks down acetylcholine into acetic acid and choline by adding water. And its function is actually attributed to its name. Its name is attributed to its function, sorry, because acetylcholine actually breaks the ester linkage within the acetylcholine molecule, which causes the formation of these two products. So with respect to structure, we have an acetylcholine molecule over here, and it basically consists of 4 subunits, just that one is being blocked by the other. So we have 1, 2 here, 3, and 4 here. Each of the subunits has 2 different binding sites. The first is the peripheral binding site, which is basically this gorge here, where the acetylcholine molecule is able to enter, and it basically consists of 14 aromatic rings that form a very, very strong and highly negative charge. And then the second binding site is here towards the bottom of that gorge, and it's called the catalytic binding site. And it consists of the catalytic triad composed of the side chains of 3 amino acids, glutamate 332, histidine 447, and serine 203. The serine 203 is really important in this molecule because it basically acts as the knife edge and initiates the catalysis reaction of acetylcholine. So here we have a depiction of a drawing that I did of the internal structure of acetylcholinesterase. So basically this line here is just going to represent the polypeptide backbone that keeps these 3 amino acids together. And over here we have all of the negative aromatic rings that line the side of that gorge that create that really, really strong negative charge. And then down here we have our catalytic triad consisting of glutamate 332, histidine 447, and serine 203. You can see here that all of the amino acids, all 3 of them, are actually stabilized with each other by associating weak bonds with their side chains. And so for our mechanism, of our reaction, it basically starts off when acetylcholine gets close to the entrance of that gorge. And what happens is that the positive charge on one end of the acetylcholine molecule, because the nitrogen is strongly attracted to that negative charge in the gorge. And what happens is that this negative gorge here is actually able to orient the acetylcholine in a position right over the serine 203 to initiate that reaction. So serine, what it does is uses its hydroxyl group, which is loosely associated with this hydrogen. And what happens is that the oxygen attacks the carbonyl carbon of the acetylcholine. And at the same time, the oxygen of the acetylcholine grabs and picks up that proton here. And then what happens is that ester linkage begins to dissociate and break between the oxygen and the carbon of the acetylcholine. At this time, we have a huge amount of water molecules within this gorge. However, I just omitted drawing them just for the purposes of being able to see this reaction. And what they do is they actually stabilize the histidine and glutamate. So that way they stay stable and the reaction can continue. So when that happens, basically an intermediate is formed and a serine acetyl intermediate is formed. And this formation actually causes the conformational change of the enzyme, which allows the release of choline from the gorge. And at the same time, the hydroxyl group of the water being held by this histidine attacks the carbonyl carbon of the serine acetyl intermediate. And that serine acetyl intermediate actually uses its oxygen to nab that proton and restabilize its bond with the histidine. And then once that is complete, the acetic acid is finally formed and then released from the gorge as well. The amino acid side chains are all stabilized with each other again. And acetylcholinesterase is active again and restored to its active state where it can undergo another reaction with another acetylcholine molecule. So here we just have a picture of the acetylcholine subunit. It's just one subunit here showing you that catalytic triad. And here's just a closer version with the aromatic rings that would line the gorge. So this is really important in helping with prevention of some diseases, particularly Alzheimer's disease. So Alzheimer's disease is a neurodegenerative condition in the brain caused by low levels of acetylcholine in the synapse from binding to their receptors. And this can actually be worsened over time because the lack of the acetylcholine within the synapse and binding to the receptors can cause the loss of these acetylcholine-dependent neurons. So it's commonly seen in elderly people, 65 years and older, and affects 2/3 more women than it does men. However, we don't know why. It's just more commonly seen in elderly women. So it's the single most common cause of dementia being the decline of cognitive and non-cognitive function, which is seen by forms of impairment in the long and short-term memory, language skills, problem-solving skills, and thinking abilities. And unfortunately, it can significantly impact a person's behavior, their quality of life, and the people around them. So we can basically think of it like this, bringing back our little Pac-Man again. What happens is that there is basically a decrease in the production of acetylcholine in the neurons. And what happens is that usually when there's a normal amount of acetylcholine released within the synapse, the acetylcholinesterase just eats up the leftovers. But with a decrease, acetylcholinesterase basically works overtime and degrades more than it's supposed to. So these acetylcholine molecules actually have less of a chance of binding to their receptors on the postsynaptic neuron, which brings about the onset of the symptoms. So the causes of Alzheimer's, unfortunately, we don't know its pathogenesis. However, we do believe that it may contribute, genetic susceptibility may contribute, as well as some environmental triggers. Mechanisms are also currently unknown. However, we do speculate that the accumulation of beta amyloid protein and abnormal tau protein can cause disease onset, as well as oxidative damage and slow inflammatory processes within the brain. Unfortunately, right now, there is no cure. However, there is treatment in the form of certain medications. That medication is specific, the specific medication being donepezil. Donepezil is an acetylcholinesterase inhibitor. It's a piperidine derivative and inhibits the hydrolysis of acetylcholine, and its resulting effects are basically the increase of acetylcholine within the synapse to bind to those receptors on the postsynaptic neuron. It can reach its peak concentration 3 to 4 hours after oral ingestion from 1 to 10 milligrams per day, and it's eliminated as waste through the kidneys. So for donepezil, its mode of action basically consists of that permanent positive charge on its nitrogen that is basically attracted to that aromatic gorge. And what this does is it basically orients the molecule towards the catalytic triad, where the oxygens here can bind with the serine 203 and histidine 447, blocking any other acetylcholine molecules from entering. So here we just have a subunit with our donepezil, and in here is where the donepezil would sit. This is the nitrogen here with our red oxygens here, and you can see how that bond is stabilized with the serine and histidine of the catalytic triad. So basically what this results in is, because of our decrease in acetylcholine, we have the release of the acetylcholine in the synapse. And what you can think of donepezil as is that little ghost in Pac-Man that basically stops him in his tracks. So what that ghost does, donepezil does, is bind to acetylcholinesterase, stop acetylcholinesterase from catalyzing the breakdown of acetylcholine and leaving more acetylcholine within the synapse to bind to the receptors. So that's all I have for my presentation. Thank you for listening, and I hope you learned something about acetylcholinesterase.